is okay. This is it. I guess if I start talking, the other three will turn up. So here it goes. It's a little bit unfortunate that they aren't here because this is going to be a pretty challenging, if not the most challenging thing that we've done so far. We are starting chapter 8, and we are looking at what's called hypothesis testing. And 8.1 is an intro to that. And so you say, oh, I wonder what that means. What is hypothesis testing? Well, it's a statistical process. It's a standard process that we use in statistics to find out, inverted commas, what the truth about a statement is. So I'm going to give you an example without going into too much of the theory, just to show you how you would do a pretty standard type of hypothesis test, right? So imagine I make a prediction. I make a statement that I would like to be able to prove. And my statement is that Scottish people's age, I guess I should say average age, is more than 35. There we go, one of our latecomers. So my statement is, I would like to prove that on average, Scottish people are older than 35 years old, right? So that's quite an old country, but actually that's not unreasonable. The demographics of Scotland and a lot of Western Europe are getting older. Fewer children, people live longer, average age goes up. So I would like to test that. So how would the statistical process go about? Well, the first thing is that we try and formalize this statement. And we do it by having two distinct statements, and they're called H0 and HA. Although the book calls this second one H1, I do not like H1. I'm going to call it HA. It's the same thing, it's just a different name. And these are the two statements. HA is called the alternate hypothesis. And that's the one that I've made here, right? So the average age of Scottish people is more than 35. The average of a population is new, and I'm saying it's more than 35 years old. So whatever statement you're going hunting for, it always goes here, right? Now the other one, the top one, it's called the null hypothesis. So you're learning a whole load of jargon at the same time. And the null hypothesis is that the mean population is 35. So we're comfortable with how this statement generates these two. This is the formal way of making that into kind of statistical form. Now, I'm coming back to this question, but I wanted to get good at this. So I'm going to give you, there are only 3 hypothesis tests in the world, right? Only 3 different kinds. And I'm going to give you an example of each and show you what it would set up like. So suppose I had a different one and I wanted to say that the IQ of Americans, right? I should always stick the word in front, average. That the average IQ of Americans is less than 105. I guess I should put it in English. Less than 105. Well, in that story then, you'd have a null and alternate hypothesis, and you'd say the average, the mean of the population, is less than 105. Do you see where that comes from? And what would we write down for the null? We would make it equal 105. And when you have a statement that is a less than, we call these left-tailed tests. So that's the first story. Suppose I had a different story. Suppose I wanted to say that the average height of OC students was less than 72 inches. Well, in this case, right, you'd have your usual guys. Now, oops, I did less than. I don't want less than, I've done that. Let's do more than. So I'm going to have to make this a little bit more realistic, more than 65, right? So the average height of OC students was more than 65 inches. More than 65 goes there. And equal goes there. So far, so good. Now, there's a third and last possibility. Pick some other story. The average number of children in a American family is not 4. So it's not or not equal to 4, but they would normally just do not 4. So we have got one last hypothesis test for this. Now, when it's less than, you write that. When it's a more than story, you write this. But when it's a not equal to story, what do you think you write down for the last situation?
Probably
that. Right. If you've not seen that, do you know if you put a stroke through the equal sign, it's actually a symbol and it means not equal to. And as always, that's 4. Right. So if I just gave you a story, you know, like these 3, do you feel comfortable you could generate the H naught and the HA? So let's take that out the picture and return back to my story here. Null hypothesis, alternate hypothesis. And that's step 1. Step 2, you're going to collect the data. Right, if I wanted to prove that the average age of Scottish people is older than 35, right, more than 35, then what I would, well, I guess I could ask all of them, but that's impractical. So what I would probably do is I would get a random sample. And let's suppose I get a random sample of 200 Scottish people. And I found out what the average age of those were. And the answer I got was 36 years old. Now, at this point, a lot of people, unfortunately, would say, hey, you don't need to anymore. Look, your average is 36. It's bigger than 35. That's the evidence that you were looking for to prove that what you said was true, right? Right, 36, bigger than 35, I proved it. Well, not really. This particular sample was 36. Do you know if I got another sample of 200 people, couldn't I have got 34? And then another one, 34.2, and another one, 35.1, and another one, and so on and so on. Couldn't that just be a lucky one? Couldn't that just be a 1 in a, you know, 1 in 100? I picked a lot of older Scottish people, right? So that doesn't count as evidence, not strong evidence anyway, right? That's why we need this hypothesis testing. We have to put in a little bit more work to come up with more acceptable decisions of, yeah, you're right, that is true. You've proved it to me, right? Or not, as the case may be. Now, in these questions, the ones we're going to do, we're going to assume that we know the standard deviation that it's 15. Right. So you collect a sample of 200, the average is 36, and you know the standard deviation of the population is 15. Okay. And then there's a guy that you pick. And he's given the Greek letter alpha. And this alpha is called the significance level. And I want you to think of alpha as being the probability you get it wrong. Since you don't ever do anything in statistics that's 100% right? You don't do 100% confidence interval, right? Don't you do a 90% confidence interval or a 95 or a 99? So alpha is the probability that you're going to get it wrong. Now you want that to be nice and small, don't you? You don't want to get it wrong half the time, because that would be an alpha of 0.5. So what are the typical numbers that are chosen? Well, there's a 10% alpha. We use the decimal value for it. There is a 5% alpha, significance level, and there is a, at least for us, there's a 1% alpha. Can you see that in this storyline then, if I decide to do a hypothesis test with a significance level of 10%, any conclusions I get to saying, oh yeah, this is right, you proved it to me, do you know that's going to be wrong 10% of the time? So that's what we're figuring out here. How much do we want? Well, if you want this, right, I'm only going to be wrong 1 in 100 times, then you may not be able to prove this all the time. Right? You may be able to, you may, I can't prove it. It might be right, it might be wrong, but I can't say it. If you do 100. On the other hand, if you do a 10%, isn't there a chance you might get more often? Yeah, you're right, you proved it. So there's a kind of balance between getting some significant result or making it so high a hurdle to climb over that very few times do you actually get any significance out of your information. So are we cool on this? Sample, mean, and this magic guy called alpha, which won't actually be used until virtually the end of this process. But we pick them here before that happens. So far, so good. Now, there's only 4 steps, but step 3 is huge. There's a lot in step 3. In step 3, we are going to find what's called the p-value. And the p-value is essentially the probability that your sample, X bar, or bigger, or sometimes less, depends on the story, could have happened by random chance. So we're going to find out how likely could you get a sample of average of 36 in a population that was 35. How likely is that to happen? Now, if the answer is that can happen about 40% of the time, then we don't have evidence, because that would happen a lot. On the other hand, if it only happens 1 in a million times, isn't that so unusual that it wasn't random? What that is telling us is that we now have the evidence we're looking for. So this thing called the p-value is basically a number that you want to be really small. The smaller, the better. Because what that means is that this did not happen by chance. This happened because this was true. Okay? So a tiny p-value means that you didn't get this sample by chance. You got it because this is true. So that's the logic behind what a p-value is for. Well, how do we get a p-value? Well, that's a little bit more awkward. I'll show you its formula. It's the probability that you get a z-score, right? Oops. Let me redo that. Let's just tell you how to get the z-score first. There's too much going on here. The z-score is x bar, oh dear, my brain, mean take away x bar over the standard error. The standard error is going to be the square root of sigma over n. So the z-score is, this number is 35. Oh, I am getting old. I was right the first time. My apologies. I know what the problem is. I'm thinking ahead to that next line, and I shouldn't do that. So it's x bar, take away mu over the standard error. Hope I haven't thrown you too much. Now, the standard error, the guy that's going to go on the bottom, is sigma divided by 200. So I can put that down here. Now I can either turn it into a decimal right now, or I can just leave it alone and let the calculator do it all in one go. So we're going to get this thing called the z-score, and this z-score is then going to get me the p-value, right? So that's kind of the order that we need to do this. Now, if you want to do this in your calculator, you need to put a bracket around it. So here's my calculator. Actually, let's use the emulator. Okay, so you should be seeing, oops, wrong one, a big calculator in a second. Are you looking at a big calculator? Right. So let's see if I make it any bigger. There, that's as big as I can make it. You still looking at a big calculator? Right. So the calculation was bracket 36, that's the me x bar, take away 35, close the brackets, divided by the standard error, which is the square root of sigma, which was 15, divided by 200. And the answer I get here was 3.65. Are you okay with how I got this number called the z-score? Okay, we've got hands up from Valerie. So what we're going to now do is return back to my notes and take you to the next stage. We are now going to get the p-value. The p-value is the probability that you get a z-score greater than 3.65. Now you might say, why is it greater than, or couldn't it be less than? If this thing says greater than, this will say greater than. If this says less than, this will say less than, okay? And as if that wasn't bad enough, this thing, you have to use your calculator to calculate. So it's going to be a guy called normal CDF. And then the format is going to be small number the big number, 0 and 1. And in this particular case, to get the p-value, because that's what this is going to calculate, the small number is going to be 3.65, the big number is going to be 9, 0 and 1. That's how you find the z-score greater than this number. That's the probability that you get a z-score greater than this number. So let me show you on your calculator where you get this guy. On your calculator, above the variables button, there's a guy called distribute. So you go blue button and you hit this guy. The choice I want is choice number 2. So that's how you get to normal CDF. So you hit, show you again, second button, variables, that gets you distribute, choice number 2, and you hit enter. And then you type in the numbers that I've written down, 3.65, comma, 9. And if you're wondering what the 9 is, I just pick a number bigger than 3.65. So I could have picked 99 or 1,000,004 if I felt like it would still work. Then you do comma. 0 is because the z-scores is a normal standard deviation, a standard distribution. So its mean is 0 and its standard deviation is 1. Those two numbers are fixed, they're always that. Now when you hit it, you are looking at a really small value for p. The p-value is roughly 1.3 e to the negative 4. We're almost done. Almost got this thing finished. Has any of you in other classes, maybe chemistry or physics, came across this weird thing that happened when you were doing a calculation on your calculator? Doesn't it just mean it's a very small number? In scientific notation, it means 1.3 times 10 to the negative 4. The easy way to think about that is that this thing here tells you how many zeros. 4 of them, including that one. And then you just fill in. So it means that decimal. So when numbers get really tiny, the calculator resorts to this scientific notation format. So, I mean, if that was e to the negative 6, wouldn't you do 0 point, a lot more zeros, 1, 3. So that's step 3 finished. That's where you're going to have the most help, the most work.
So I got a question. We can always pick number 1 is the z-score you've calculated, the first number. The second number, you're just randomly picking a number at choice? I'm
picking a bigger number than that. So anything bigger than 3.65. Let's just call it 9 all the time. That way you will be safe.
Okay.
So these last 3 in this question, anyway, these last 3 are going to work out fine. So now we're going to have to do the final step. And the final step is the test. We ask ourselves this simple question. Is this p-value less than the significance level alpha? Now, I should have actually picked one of these. So let's pretend I did that. Which one of these alphas do you want to pick? Just so that we can continue this. That one, or that one. In the question, they always tell you what it is, but what do you want?
10% fine.
Number? I didn't catch it, that's all. What did you say?
10%.
Okay, 10% it is. We're picking that one, right? So, is the p-value less than alpha? Is this fella less than that guy? And do you know the answer is going to be yes or no? Right, it is less or it's not. Would you agree in this case it is less?
Yeah.
And that's good news, because what does that mean? I have now shown or proved that Scots people's average is more than 35. Because if your p-value is so tiny that it's really unlikely that you got what you got here by randomness, then it must mean that this here is telling us that that's likely to be true. So you would say, that the alternate, HA, which in this case is that guy, is true. Or more likely in English, you would say there is significant evidence to prove that the average age of Scots guys is more than 35 years. So if you ever hear someone talking about a new scientific discovery, they will almost always say they have significant evidence, or they have found significant evidence to prove something is true. And that word significance is kind of an indication that they have done a hypothesis test in some way. So it's very important that we have a formal way of doing it. And the reason we have this is everybody in the world who does statistics follows this pathway. They do it the same way. So that when you do an experiment, I can go back and check your numbers, and I can, redo the process. And at the end, I will come to the same conclusion that you did, right? There's evidence to prove in this case that Scotsmen are older than 35. And that's very, what's the word to look at? That's very important, because what it does is that we now have a formal way of deciding the truth, rather than people arguing about, yeah, 36 is big enough. That's enough, right? That's too vague. Because it could have happened, and it will happen. Can you imagine a different situation where this p-value was 0.6? Right? Well, wouldn't the answer here be no then? And what does no mean? No means you haven't found any evidence to prove that this is true. Right? You haven't got any evidence. So in the legal system, can you think of it as one of them is you're guilty and the other is you're not guilty, right? So if you get enough evidence, you're guilty. And if you don't find enough evidence, then you're not guilty. So these are the guilties and these are the not guilties. No, that's maybe a good analogy. Okay, we've seen the first process, start to finish. And I'm going to do hopefully 2 more. And what I want you to pick up from this is that once you know the process, you just repeat it with different numbers, right? So let's suppose our next story is going to be that the IQ, the average, keep missing that word out, IQ of Americans is less than 105, right? So we are looking for evidence to prove that the average IQ of Americans is less than 105, okay? So step 1. What will the null hypothesis be, the top one?
105.
Equal to it, yes. Great. Now, for this story, what will the alternate hypothesis be? Well, you read this and you try and make it look more mathematical. So the mean IQ Listen.
Yeah.
Are we good with step one again? Do we feel happy about there's some statement that we're trying to prove is true, and that's generated a null and alternate hypothesis? Are you comfortable about the, how it's set up and the number that I used and the inequality that I used? Are we good, guys? Okay. Step two. Getting dings from somewhere. Let's collect the data. Oops. Need to collect the data here. So I went out and I collected 300 random Americans and I found out what their IQ was, and it ended up being 104.1. And the sigma for IQs is 10. What significance level do you want us to do this test at? The last one we did, I think, was 10%. So what are we going to pick this time?
5%.
Okay. So this is going to be a 5% significance level hypothesis test. So this is given to you in the story, right? It's not like you go and calculate it. You're told it in the story, right? So now we're on to the big job, right? This is where all the points are. This is where all the work is. Don't we have to get a Z-score? Only this time I'm going to get it right. That's the Z-score. In this case, we have an IQ of 104.1. Take away this fella, which is 105, and it's divided by the standard error, which is sigma divided by n. Are we comfortable about where I got these numbers from? Right? Pretty much the same as last time. Now, this guy is going to be negative. I know that right now. I can just tell looking at them that we're going to get a negative answer, and that's okay. Negatives happen. So I'll do a little bracket over a little touch, and it's going to be 104.1 take away 105, close the brackets, divided by the square root of 10 divided by 300, boom, boom. And I got negative 4.9 to 95. I'm going on forever there. There's our Z-score. Now we're going to get a p-value, and it's a probability that you get a Z-score. Right. Now in this case, it's going to be less than that number. I'm just going to call it 4.9. Yeah, you said, but the last time it was bigger. But do you notice this says less than 105? So we're looking for Z-scores that are small and negative, right? So it's less than this number. Now, that fella is going to be a normal CDF. And the generic version of this is the small number, the big number, 0 and 1. Now, the last time it was a number, 9, but this time we're going that way. So we are looking at things that are less than 4.9. So you see it's negative 9, negative 4.9, 0 and 1. So if you are looking for a greater than situation, which is what the first question looked like. See if I can find it. Greater than this guy, 9. You want less than? -9. Do you see the difference? Right. Now, this is going to be done in our calculator, and I strongly suspect it's going to be a tiny number. Let's see how tiny it is. Second distribution, choice number 2. The numbers are -9, comma, -4.9, comma, 0, comma, 1, close the brackets. And I have a 4.8, if you round it off, e to the -7, which means 4.e times 10 to the -7. This number is so darn small. You could probably win the lottery more likely than getting that sample from this world. That is extremely tiny, which is good news, because don't we want really small p-values as evidence that this works? So step 4 of the test. Is our p-value less than alpha? Is this guy, with 7 zeros in him, less than the alpha that we chose, which was 5%? And I'm pretty sure that's another yes, isn't it? And when it's a yes, that means we can say that HA is true. In English, we would be able to say there is significant evidence to prove that the average IQ of Americans is less than 105. So if this was actually real data, I could then, go to a medical journal and say, do you know that the average IQ of Americans is less than 105? I don't think that would get an awful lot of shocked faces, but I've at least proved something, right? I've proved something statistically as valid as true. Now, do you notice the difference between a greater than or less than? There's a difference in this fella here. But apart from that, the rest of the process is pretty much the same. Agreed? Okay, so I'm now going to create a third story. And I'm deliberately going to create one that doesn't work. By that I mean we're not going to find enough evidence to prove something, just to show you what that would look like, right? Because not all your answers are going to be, yeah, you're right, you've proved it. Some of your answers are going to be, nope, you haven't proved a thing. So for my third one, I'm going to do the average points scored by an NFL and NFL team is less than 23 points. And that may be true, but I'm going to make sure that it's not, right? So the average, I'm going to go searching to see if I can prove that the average points scored by an NFL team is less than 23 points. Okay, let's start. Less than 23 equals 23. You comfortable with that one? Right, next one is made up data. You're told this in the question. They collected a sample of 20 teams and found out, how many points they scored. And the number of points they managed to score was on average 22.6. Which is definitely less than 23, agreed, but it could have just been luck. Let's suppose we know that the sigma value is 5 and they tell us, and we are going to pick a 1%er. So there's step 2. So far, so good. Right. Now, let's get a Z-score. Hopefully, the more we do this, the more comfortable you get used to the pieces. That's 22.6. Take away 23, divided by the square root of sigma, which is 5, over 20.
Negative 0.8.
Negative 0. Where?
Oh, I was just telling you the answer.
Oh, you're ahead of me. Negative 0. What?
8.
8. Okay. So p-value is going to be the probability that I get a z-score. Now you have a decision. Is it z-score bigger than this or z-score less than that?
It's going to be less.
Right. Are you getting a little bit more comfortable about how you know which direction to go?
Yeah.
And there is another one. When z-scores are negative, it ends up being less than. And when z-scores are positive, it ends up being more than. You can almost tell just because it's positive, it's going to be bigger than a positive number or less than a negative. That's pretty common. Right, in this case, it's going to be a normal CDF again. It's going to be big, small, 0, and 1, right? Now, this is a less than story. When it's a less than story, don't you put the -9 and then the -0.8? Right, that's the order. And now we go in here and we go hunting for that guy. Second distribution. Oops, just went off on me. Clear that out. Second distribution, number 2. -9, comma, -0.8, comma, 0, comma, 1. And the answer that we get is 0.212, right? So it's 0.212. We have now found the p-value. And that is step 3 done. Looking good? Right, step 4. Let's do our test. Is our p-value less than alpha? Is our p-value less than this guy? And the answer is no, right? So what does that mean? Well, that means there's no evidence to reject H0. That's just how you would say it statistically. What does that mean in English? There is not enough evidence to prove whatever I just said there. Blah, blah, blah. American football team. Now, the fact that we're saying there's not enough evidence to prove that this is true is not the same as saying this is wrong. It just means there's not enough evidence to prove it's correct. It may be true, it may be wrong. We don't know. That's pretty much all it means. So don't put any extra meaning on a no. Don't think that a no means that it is 23 or that it's not less than 23, or for that matter, it might even be bigger than 23. All that that means is there's no evidence to prove anything. We don't know. Analogy. Do you know when you have someone who commits a crime and the verdict is not guilty? Does not guilty mean that the person definitely didn't commit the crime? No. Doesn't it just mean, if you turn it on its head, there's not enough evidence to prove that you did commit the crime? Because aren't there some guilty people who get off? Right? Of course, aren't they innocent people who end up in jail? And those are errors, right? When either of those two things happen, that means you got it wrong. And we do not like getting it wrong, but it does happen. And so what I want to do for the next bit is to now look at some of the theory behind hypothesis testing, right? Here are the three main situations that can happen, right? IQ less than 100, IQ greater than 100, IQ not equal to 100, right? That's the three standard ones. I think we've done, what, 2 of these and 1 of these, and I haven't done 1 of them yet, but we can do 1 of them probably on Thursday, right? So a less than, can you prove to me it's bigger? Can you not equal? If you want to visualize what does a p-value look like, it's basically saying, what's the chance that you got a sample of this kind of number or less? And that's called a left tail test. You see that's on the left side. And this one is, what's the chance that you got a sample and this size or bigger, right? It's going that way. And that's a right-tailed test. The smaller this is, the more likely this thing here is true, right? The alternate will be true. And a two-tailed test just means, you know, it could be, you know, this side, it could be that side, but it's small, whatever it is, right? Are we okay with that, kind of the general visualization of a left, a right, and a two-tailed test, as they're called? So we've done, I think, 2 left tails and 1 right tail. Now, let's look at errors in hypothesis testing. There is a decision that we made. And then there is the truth. And in the truth, you have H naught and HA. And in the decision, you have your kind of H naught and your HA. And if you put them together, there are 4 things that could happen. The truth is H naught is true, right? Let's put some numbers beside it so we can kind of visualize it. Right. Here we go. We'll use this one. The truth is that that is true. Imagine that was the truth. Somehow we knew it was the truth. We made a decision based on our sample and we said that guy. Right. That's good news, right? We got it right. So I'll put in the words correct. We got it correct here. Now, couldn't we say the alternate was true and the truth was you were right? Wouldn't that also be an example of being correct? What about H naught is true, but your decision was to accept the other thing? So this was true, but you said that. That's a mistake. That's an error. And we call that alpha. Yep, our significance level, alpha. And that's also called a type 1 error. This guy, you got it right. These always add up to 1, right? So if this is 0.2, this is 0.8. If this is 0.1, this is 0.9, right? Now, the other situation, this is true, but you've made that. That's called beta. And this guy here is 1 minus beta. And this is also an error, and this is called type 2. So very theoretical, right? It's full of H naughts and HAs and alphas and betas and special names for them. So let me try and give you an analogy that might help you figure out what these are. Down here, we've got the truth. And up here, we've got the verdict. And the truth is, the guy did the crime. And the truth here is that he didn't, right? So there's some crime, and this guy's been picked up and goes to trial. And the truth is he did the crime, right? And this truth here is he didn't do the crime. And then there's a verdict. And in the verdict, don't you have he was found guilty or he was found not guilty? This guy here that I'm calling Alpha, isn't this a guy who did the crime but the verdict was not guilty? Wouldn't that be a guy who walks away free? Did the crime, couldn't get enough evidence, he walks. We don't like that, right? We want that to be tiny, don't we? You know, you want, I don't know, 10% of the people who did the crime to get away with it, right? We want to convict 90, right? So can you imagine that was 10%? Then wouldn't this be 90? So you'd get it right, 90. Now what about the other case? Somebody who didn't commit the crime. Well, didn't commit the crime and going not guilty, that's good. We like that. But if you get it wrong, you didn't commit the crime, but you were found guilty. And let's suppose that was 10%. Can you see the two kinds of errors? You say one thing, but the opposite is true. That's an error, right? Now, alpha and beta are like these two errors, right? That's what they are. If you want to make one of these smaller, you're going to have to make the other one bigger. And that's just nature. If I want to make sure that I reduce the number of guilty people who go out of jail, right? Now, how I might do that is I might make the rules of evidence a little bit less. So instead of saying, look, instead of being beyond reasonable doubt, you change it to just beyond, I don't know, try to think of a word beyond reasonable, beyond very unlikely doubt or something, right? You just make it, you make it so much harder to get off with it, right? So the guy only needs to be there when the crime happened, and that's good enough, right? You're in jail. Because if you convicted somebody like that, won't this number reduce really quickly? But won't you end up putting a lot of innocent more people in jail? Right? If the only evidence you need is to be there when the crime was committed, even if you just happen to be walking by, you know, when the mugging happened, you know, oh, you were there, you're guilty, right? If you make this guy smaller, you're going to make this guy bigger, right? See, to make sure you don't put innocent people in jail, aren't you going to have the bar quite high so that innocent people don't very often get caught? Now, I mentioned this to my other class, in every law or legal system in the universe that we know of, these are never going to be zero. Aren't you always going to have some innocent people in jail? I mean, just sheer bad luck. Or maybe a witness tells a whole load of lies and puts you in jail. Yeah, I saw him, he shot my brother, he's guilty as heck. I could put you in jail, right? Of course, if you make this too big, right, won't you end up with a lot of them? And if you make this, you know, the other way, you make a lot of them. Do you know the only way you could make this zero? Suppose this is the law system. You live in a country where when someone gets charged with a crime and it goes to trial, you always come back with the answer, not guilty. Won't that be zero? Of course, won't society degenerate into a total shambles? Because nobody that's guilty will ever be convicted either. Agreed? So societies have to decide the merits of these two errors and which one are they willing to live with so that the other one can be smaller. Now, you would hope in a just society, you would err on the side of safety and make this quite low and just live with the fact that you're going to have a lot more innocent, guilty people go free. But you don't want to make it too lenient, because don't you just get people who commit crimes, come out of jail, commit another one, come out of jail. They don't go to jail, right? They just commit a crime, have a trial, come back out and commit it again. And they know that the chances that they're ever going to be convicted is so small that it's worth the risk. And that is the end of that. Okay. So for my next one, I'm going to do a two-tailed, right? A not equal to story. And that will cover the third possibility, right? So we're down. A scientist believes that a scientist we want. The average weight of salmon is not 5 pounds. Not the most direct, you know, scientific breaking piece of information. But anyway, he believes that the average weight of a salmon is not 5 pounds. Now, he's not saying it's bigger than 5 pounds. He's not saying it's less than 5 pounds. He's just saying he's pretty sure it ain't 5 pounds. So that is going to be what we call a two-tailed test. Right? And that's the one that we haven't done yet. So not equal to 5 gets you that guy, right? The not equals. And this fella here gets you 5. So far, so good. It's pretty much the same as the other two. So he goes and collects some data. And he collects 100 salmon, because it's a nice round number. And in this 100 salmon, he weighs them all, and he gets the answer that they weigh 5.6 pounds. Would you agree that that's at least evidence that it's not 5 pounds? It's bigger, it's 5.6 pounds. It could have got 4.8 pounds, and that would have been evidence that it's not 5 either. The sigma in this story is 2 pounds, because you're told it is. And the significance level is 0.01, because you were told it was, right? You were given this. So far, so good. It doesn't look that much different than the other two situations. Let's do Stage 1 and 2 done. Let's get a z-score. In this case, it's 5.6. Take away 5. That 5. Square root of sigma divided by 100. Let's see what we get here. 5.6, take away 5, divided by the square root of 2 divided by 100, close the thing, and I get a z-score of roughly 4.24. I can tell you right now that that is going to be significant. What is the, it's a while back, but you remember when we calculated z-scores, you know, Janice got this in math and George got that. Remember when we did those? What was the kind of range that typical z-scores would be in? There's a kind of number range that almost all of them are in.
-3 to +3.
Right. So anything that's beyond that, isn't that an outlier, an exceptionally unusual? Can you see this as an outlier? It's an exceptionally unusual. So I kind of know that this is going to finish, you know, with a significant result, but we keep going anyway. In this case, the p-value then is going to be the probability that I get a z-score bigger than 4.24 or less than 4.24. Has to be one, can't be both. This is
Can you choose on this one?
Well, I know this says no equal to, and that doesn't really help me here, right? So what I use instead is the value of this. If it's positive, you go greater than. If this was negative, I would just do less than. Actually, you can use that same rule, can't you, for the other situations as well? Because it pretty much ends up a positive number, the z-score bigger than a positive, and when it's a negative number, right, z-score less than a negative, right? So that's going to be a normal CDF. Bigger than 4.24 goes 4.24, somebody, 0, and 1. Who's the somebody? What number?
Anything bigger than 4.24.
Yeah, so I'll just pick 9 because I like 9. You can pick 22 if you like 22. Now that's calculator time. Second distribution, choice 2, 4.24, comma a 9, comma a 0, comma 1. And we are looking at 1.1, 1, e to the -5. Can I just go 0.1, 2, 3, 4 more zeros and a lot of ones? Okay, so there's our p-value. Time to do a test. Is our p-value less than alpha, right? Agreed. Unfortunately, when it's a two-tailed test, there's a little tweak you have to make. And it's part of the game, you just have to know it. When it's a two-tailed test, it's a p-value less than twice whatever alpha is. Why do you think they double it and only double it in this case? And if you imagine a little picture of what a two-tailed test looks like, it might give you a clue.
There's 2 tails.
There's 2 of them, right? There's the left bit and the right bit. So 2 alpha covers that. So the p-value is 0.0000, lots of ones, less than that guy. It made no difference whatsoever. Agreed, it's still yes. Yeah, doubling up never really caused much damage. And so what we can now say is there is enough evidence to reject H0. Or in our world, that just becomes there is enough evidence. I guess I should have said the word significance, but too late now. I should have said there's significant evidence to prove that the average weight of salmon is not 5 pounds. So we can do a greater than, we can do a less than, we can do a not equals. Every single one of the stories that are going to happen in the future are going to be similar to one of those three that we just did, right? Prove something's bigger than 5 pounds, prove something's less than 20 pounds, prove something's not equal to 100. You know, those are the three basic questions, and we've seen at least one of each kind. Do you feel comfortable with that? Right, I am going to give you a question to try, and then we'll call it a day. And I'm going to give you a story, and your job is basically to fill in 3 and 4, right? So hopefully you got a calculator handy. So the story is, I want to prove, that Scottish people have been to England on average more than 5 times. So we're doing a kind of example that we believe that Scottish people have been to England on average more than 5 times. Actually, it's probably more than 50 times, but 5 times will do. In America, that would be better. Couldn't I say that somebody in Washington had been to Florida more than 5 times, right? That's a little bit less likely because you've got so many states, right? But that's the one we're using. And I'm telling you that they did a sample of 200 and that the sample that they got was on average 5.8, that the sigma was 2, and that you're going to use a significance level of 0.01. So you have got 6 minutes to do that question. And then I will do it with you and you can double check on it. Just get myself set up. 2's done for you, as it would be. I'll give you little clues on the road. Okay, let's see how this goes. Right, Scots people have been to England on average more than 5 times. What does HA look like, the alternate hypothesis? New. What's, in this case, 5. Agreed? 2 was given to you, so it's here. 3, the mean, 5.8, divided by 5, square root of 2 divided by 200. And I believe you get the answer 8. You know that a Z-score of 8 is even better than winning the lottery. That's how rare it is. So a Z-score of 8. Let's see where that takes us. Well, we want to find what's the chance that we get a Z-score greater than 8. So it's going to be a normal CDF. Greater than 8 is 8 to, I don't know, 9 or 900. 9s works. 0 and 1. And you should, depends on your calculator, of course, but you should get a really strange result. Even stranger than some of the other numbers. Second distribution, choice 2, 8, 9, 0, 1, close brackets, enter. I'm not even going to write that down. Wouldn't it be 16 zeros, right? 0 and 15 more. For all intents and purposes, would you agree that the answer is 0?
Yes.
Right. So that's less work, right? So my p-value is essentially 0. So time for the test. Is my p-value less than significance level alpha? Is 0 less than this case? And the answer is a big yes, isn't it? 0 is less than that. Looking puzzled, Derek. Is there?
No, we're good.
No, we're good. Okay, so what does that mean? Well, there is enough evidence to reject H0, which means that, yes, we have proved that Scottish people have been to England on average more than 5 times. In fact, based on that one, I bet you I could probably prove they've been there more than 10 times. Right? I mean, with a Z-score like that, I might even push it to 15 times. And you could certainly do that, because after you've got that, couldn't you do a test? Oh, I'll try some a bit more. I wonder if it's more than 20 times. I wonder if it's more than 15. And eventually you'd get a point where it wouldn't be significant anymore, right? You wouldn't get a Z-score that was that unusual. And that would be kind of where you should stop.